So first of all, according to quantum field theory, empty space, vacuum, there's something called the vacuum catastrophe. According to quantum field theory, the value of energy in vacuum space is approximately, the upper limit value is approximately 10 to the power of 112 ergs per cubic centimeter, and the observed value is approximately 10 to the power of minus 8 ergs per cubic centimeter. When we observe what you call empty space or outer space, we don't see any energy, but that energy has to be there. For example, why does it have to be there? Hawking's, he came up with a very famous theory called Hawking's radiation. Hawking's radiation is named after him. And Hawking's radiation is to do with black holes, mainly how black holes dissipate. It was always thought that a black hole, once created, can only get bigger. It can never get any smaller. It cannot be destroyed or disappear. So Hawking, he proved that actually it can dissipate through Hawking's radiation. So Hawking's radiation, what exactly is Hawking's radiation? Hawking's radiation takes into account the quantum froth in empty space. So in empty space, you get particles appearing and disappearing. And this happens throughout empty space. Particles appear, matter and antimatter particles. Two particles will appear, they'll come together, they'll annihilate, and so a black hole at the event horizon, right at the edge, the antimatter part of the pair will be attracted towards the black hole, and the normal matter particle won't be attracted to the black hole as much as the antimatter particle. So the normal particle will go out away from the black hole, and the antimatter particle will go towards the black hole. And the result will be that the antimatter particle will go into the black hole and annihilate a normal particle, so reducing the size of the black hole. And the normal particle, it will show up as radiation. And it is said the most efficient way of creating energy is through a black hole. If you can create a small black hole, it will give off so much radiation that you can power your systems with. It'll be like a nuclear, like a small sun, having a small sun giving enormous amounts of radiation. Now all that radiation is coming out from the vacuum. It's not coming out from the black hole. It's coming out from the vacuum. The vacuum, the particles that appear and disappear, they are being separated. The antimatter particle is falling into the hole. The normal particle is irradiating, and so we know for definite that in empty space there is large amounts of energy. Although we can't see this energy, we can't detect this energy, but we know this energy is there. And Hawking's radiation is a fine example that the vacuum has to have energy. You can argue how much energy per cubic centimeter there is. That's a different conversation. But we can say for sure that the vacuum does have energy, although we can't detect it. We don't know in what shape or form it comes in. But this thing we know for definite, that the vacuum does have energy. So on one hand you have empty space, the fabric of space, with all its quantum fields, with its the froth of particles appearing and particles disappearing, and with its energy coming down from all directions towards the center of the earth. Now, we have a little bit of a problem. The space is coming down, but it has large amounts of energy inside it. What's happening to that energy? And this was a major problem, because you can have gravity by space coming down, but where is that vacuum energy going? You have to find a reason for to get rid of that vacuum energy. Otherwise, the earth is going to heat up and become a star in no time. So this was a major dilemma. If we follow the theory of Einstein, we can say that the vacuum is coming down, but then we have to have a reason, we have to have an excuse or a theory of where that energy is going. So on one hand, we have high levels of energy in the vacuum. So let's look at the earth. So the earth is made of atoms basically containing 3 components and force fields: up quarks, down quarks, and electrons. If we look at the neutron, for example, the neutron contains 2 down quarks and 1 up quark. It's held together by the strong force. The strong force behaves in a completely novel way, in such that when the quarks are not trying to get out, the force is relaxed. But if the quarks try to get out, it becomes stronger. The further they get out, the stronger the force becomes. And the funny thing is, if you measure the mass of all the particles that are creating the neutron, they account for 2% of the mass of the neutron. So where is 98% of the mass of the neutron coming from? Again, we go back to Einstein's theory of what you call energy. E equals mc squared. Energy equals mass times the speed of light squared. So mass and energy can be replaced by each other. So the mass of the neutron is created by the actual interactions or the movements between the quarks and the strong force. The quarks are desperately trying to get out of the neutron, and the strong force is resolute in keeping those quarks inside the neutron. The activity between these two, the strong force and the quarks, is so intense, so unbelievably mind-bogglingly intense, that it accounts for 98% of the mass of the neutron. So what would happen? What would happen if those quarks stopped their activity and became stood still, for example? Straight away, the neutron would lose 98% of its mass. So it's the activity inside the neutron by the quarks and the strong force that is responsible for 98% of the mass of the neutron. This requires energy. The quarks themselves, they don't have this energy. This energy has to be coming from outside, because if this energy was already inside the neutron, it wouldn't matter whether the quarks are moving or whether they're not moving. Only when the quarks are moving and trying to get out of the shell, that's the strong force, that the mass is there. If the quarks stop moving, then the mass disappears. So the neutron has to receive a constant flow of energy, which is creating 98% of the mass of the the neutron. And when you convert that into E equals mc squared, the amount of energy that the neutron is consuming is very considerable. So the only energy that is available is the energy in the vacuum, the quantum fields. The energy that powers the quantum fields and powers the what you call quantum froth is the only energy that's available. And matter requires large amounts of energy to remain in its present form. So we can only conclude it's like a firestorm. You have a large fire, and the fire is consuming oxygen. The fire is consuming oxygen at such a rate that it creates a storm of wind blowing into that fire, because the fire is creating a vacuum. It's consuming the oxygen, removing the oxygen from the atmosphere, and a negative pressure is created. Negative pressure is created, more winds have to come, more air has to come and replace that oxygen that has been removed. And the whole process is so vigorous that you get a firestorm. The fire is consuming so much oxygen that a constant wind is blowing into that fire and taking causing a a full blown storm. So this is the analogy that we can, the only analogy that we can come up with is that the earth is consuming energy. Matter is consuming large amounts of energy. The vacuum has large amounts of energy. And when the earth, for example, consumes energy, it creates a void, it creates a vacuum, it creates negative pressure. The fabric of space replacing the part of space that has been consumed, the energy of it has been consumed. So if you look at it in you can look at it in an atmospheric type of way, that empty space is the oxygen and the earth is the fire, and the earth is consuming that oxygen and more oxygen has to come to replace the oxygen that has been consumed. The other way to look at it is like a superfluid. That space itself comes in discrete amounts, little balls of energy, and those little balls have all the quantum fields, contain all the quantum fields, and they contain a particularly large amount of energy, and that energy feeds the matter that we see, the neutrons, the protons, the quarks, the electrons. And once that ball of energy has been depleted, that ball collapses, creating negative pressure. And more space has to come and replace that hole in the what do you call, the fabric of space. A bit like, you can say, a black hole. In a black hole, we can understand that everything is being dragged into that hole. Nothing comes out. And the earth, we can say, is behaving like a black hole, that it requires the amount of space coming into it to power all the material, the matter, the atoms in it. And so this is what's basically causing gravity. Gravity is the effect, the result of this process, the process of keeping that matter intact, giving it energy, just like what do you call, a fire. Or you can look at it like a lake with a sinkhole. The water is going inside the sinkhole, and so everything is flowing inside the sinkhole. The water close to the sinkhole will be flowing pretty fast, and the water that's at the edges of the lake will be flowing at a much slower, or a very, very slow speed.